Yes, good evening, everyone. Welcome back to this session. So, this session is about a few problems based on GATE 2021 instrumentation paper, especially in the core area sensors, transducers, and signal conditioning. Okay, so I'll be taking one of the problem. It's purely memory based. The data taken may not be highly accurate as given in the examination. So, we'll get to know the complete picture within a week once we get the response sheets. So I have taken the data almost closer to what happened in the examination, what data given in the examination. Okay. So first problem that is based on this topic, sensors and transducers from strain gauges. That is a numerical answer problem for 2 marks. So we have given a full bridge consisting of all strain gauges, R1, R2, R3, R4 metal strain gauges. The bridge surprisingly got excited by a current source instead of a voltage source. Okay. The goal is to find the output voltage of the bridge. Given all the strain gauges R1 to R4 are identical metal strain gauges with a zero strain resistance of 100 ohm at 0 degrees C. Then the temperature coefficient alpha is also given for the gauges. Any metal wire subjected to change in change in temperature, okay, will have the effect of change in resistance through the alpha only, and the entire setup is given operating at 50 degrees C. So we can find out the change in resistance of metal wires due to the change in temperature as well. Okay. So now under the situation, strain is applied 0.01. Okay. It's meter per meter. That's a strain applied. E is given. Then the output voltage of the bridge in millivolt. Okay. Given the gauge factor is equal to 2. Okay. So how to answer this problem? We may think of smartly answering the problem by using an equation we have ready made for a full bridge. For a full bridge, V naught of the bridge is equal to E into delta R by R. That's for the full bridge. The big question here is, we can calculate E, even though it is current excited, we can calculate the voltage across the bridge. Okay, that's a input voltage applied to the bridge. Then we can calculate delta R by R. But the big question, which are to consider, which delta R to consider. Okay, so here in this equation, we took delta R by R. It's purely because of strain. That is equal to strain gauge factor into the strain. Because the gauge factor is equal to delta R by R divided by the strain delta L by L. That's how we took it. So here we didn't consider any temperature effect. So that's how we played with this data. Therefore, there is a chance of getting trapped if we go by this route. So let me take a different route then. So as per the figure given, R1 is decreasing when strain is applied. Strain is applied, R1 is decreasing. And here R2 is increasing due to strain. So due to strain, this is R plus delta R effect. This is R plus delta R effect. And this is also R plus delta R effect due to strain. This is R minus delta R effect. This is R minus delta R effect. What is given is R is given. That is equal to 100 ohm. That is zero strain as well as 0 degree C temperature resistance. But given a different operating temperature, therefore, the strain gauges will experience resistance change due to temperature also. So now let me talk about R1 and R4. R1 and R4 are gauges having decrease in resistance. So R1 is equal to R4. They are identical. So the resistance decreases due to applied strain. But anyway, the resistance due to temperature change is always positive. So therefore, delta R due to strain alone is negative. Treating this as a compressive strain in sensing elements R1 and R4 are. Okay, so now the goal is to find delta R due to T. Delta R due to T is, we know it is R into, R is nothing but your R naught. You can take, it's R naught into alpha T. And delta R due to this one, you can play with this. That is, yes, delta R due to strain is equal to, if you balance it, you will get delta R by R, that is equal to gauge factor into the strain. So delta R due to strain is equal to R into gauge factor into strain. This is delta due to strain, and this is delta due to the temperature. So this is R into Sg into E. So E is given, T is given, alpha given, gauge factor given, R is given. R is nothing but your R naught. Yes, you can take this R naught here as well. So this is your R naught. Then if you calculate this, this is given already. What is that? 100 ohm. This we need to calculate. What is that? 100 ohm into alpha is given 0.005 per degree C into the temperature, that is 50 degrees C. So this we need to calculate. Then this one, this is 100 ohm into the gauge factor is given 2.0 into strain applied is given 0.01. Okay, with this we can calculate delta due to strain. If we calculate this 100 into 0.005 per degree C into 50 degrees C, so it is going to be in ohms. So this will end up with 25 ohms if we calculate. And this will be 1 by 100 into 2. This is going to be just 2 ohms. If that is the case, what is the resultant resistance we are going to have here is, this is 100, this is 25, and this is 2 ohms. The net is going to be 123 ohms. Similarly, if we write the equation for R2 and R3, they are identical, but that will experience R plus delta R due to T. But instead of this minus, it will be plus delta R due to strain. And therefore, it is going to be 100 plus 25 plus 2. It is going to become 127 ohms. That's all. So now we got all the bridge elements. Play comfortably with the circuit. You won't make any fault. That's your equivalent setup now. This is 127 ohms, 123 ohms, 127 ohms, 123 ohms. Okay, excited by current source. We can find out V naught of the bridge. So take this as potential VA and this is VB, and bottom is not a reference. You can take it as a VX. What is VA? So anyway, this is 123, 127. It is 250, and this is also 250. Any strain? These two are identical resistors, therefore current will be equally divided as 0.5 milliamps and 0.5 milliamps. Then what is the current going through this 127.5? That will make a drop. So this drop plus Vx will make VA. So I can write VA as 0.5 milliamps into 127 plus Vx. Similarly, I can write VB as, there also the current is, this is the voltage. This voltage plus Vx will be my VB. The current is still the same 0.5 milliamps. So 0.5 milliamps into 123 ohms, it is in ohms, plus Vx. Then if you go for the overall output voltage, V naught of the bridge, it is VA minus VB. As simple as this. V naught of the bridges, then Vx will get cancelled. Will end up with 0.5 milliamps into 127 minus 123 ohms. Then V naught of the bridge is equal to, it's 4 ohm into 0.5 is going to be 2.0 millivolt. That's your output of the bridge. So the answer is 2.0 because the result is expected to be in millivolts. Okay. So that's how the problem has to be approached, by exploiting the fundamental of change in resistance due to temperature, change in resistance due to strain. Okay. Yes, there are more chances for this kind of problems to commit a mistake if we go by the formal route of full bridge expression. Okay, because we don't know what delta R we should take and what R we should take. Here anyway delta R will perceive as due to strain only, but R we will commit a mistake. So either it will be 100 or it will be what, 125. That question we can't answer, therefore not refer, don't refer this route. Okay, better Go by the fundamental. Find out all the resistances and simply make a circuit analysis to find the potential and conclude the problem. That's the best way. Okay. So thank you everyone. We'll update you with one more question soon.